so I'm Vinod again. I've been doing Hadoop for a long time. I have Zian Chen joining me. We are going to talk about the compute part of Hadoop 3x. So yeah, mostly all things YARN, etc. And the second session will be focusing on the storage piece, HDFS, etc. by Arpit and Hanisha, right? And you know, for those of you who know, Hadoop is a bunch of different things, even the core Hadoop projects, right? And YARN, the compute piece, is part of the larger Hadoop release. So before we talk about what YARN is, we have to actually set the context for what Hadoop itself is in terms of the releases, right? We release HDFS, YARN, and a bunch of other smaller things, and the list is growing. We actually release all of them together. And as he mentioned, right, December last year, the Hadoop community voted and released 3.0. We followed that up with the 3.1 release in April. So it helps to understand the overall context on what the releases are and what things are happening there, right? Even dialing back a couple more releases before that. So 2.8.0 was one of the big major releases since the 2.6 series that happened in March 17. Again, the list I have here is only focusing on the YARN piece, but it helps you just generally understand the timeline of releases, right? The Hadoop community did a 2.8.0 in March 2017, and then in November 2017 there was a 2.9.0. Parallelly there was a release train for 3x. We wanted to say let's continue the 2x release train and have the innovation train going on with 3.0, and that all culminated with the 3.0 release in December 17, and in this year we did a 3.1.0. In terms of community itself, again, the context here is we're looking at large-scale production clusters. So if you go to any rest of the world, most of the Hadoop customers are on 2x series, and it's either 2.6, 2.7, or many of them 2.8, right? So the rest of the stats that we're showing here is kind of showing how things have changed from that world, which is 2.8, 2.7-ish, right? So in 3.1.0 itself, from 2.8.3, so that was the last release we took as a baseline, there have been a total of 3,700 cheaters. And it's crazy if you just compare that release time. So if somebody's looking at upgrading from 2.8.3 to 3.1.0, the amount of content you're looking at is super massive, right? And specifically, even just comparing 3.0.0, which got released late last year, itself is still very significant. So lots of, yes, sure. There you go. Yeah, lots of crazy things happening in the community. This is another thing that I usually do to generally understand the health of a community. You need to understand who's actually contributing, right? And this graph, I've done a lot of sessions, summarizing these community contributions, and this kind of graph has never changed. There's some sort of a power law where there's a small number of people who actually contribute like massive crazy. They don't have any other thing to do in their lives, right? But then it doesn't stop there. It's not like there's a massive fall off. There's a large number of people who contribute with small things, and they're all valuable, right? Every contribution is welcome, and it amazes me that this long power law kind of structure continues to hold even after what 11 years now, right? So that's something that really makes me happy, right? Because the success of an open source story in the real long term, if you have long term view, is not the original set of people who contributed the key piece of code. It's about how the community picks it up and makes it their own, right? And this graph, release after release, it shows that, hey, there's a healthy community going on. It's not like somebody dumped a bunch of code in the open source and claimed that, hey, it's all open source community driven, right? I just want to add that. Back to the 3.1.0, another way of saying it's crazy. So the number of files changed. So we actually added close to 1 million lines of code between 2.8.3 to 3.1.0. I don't know how much that. Maybe that represents 30% of the original code base. So that's again massive, right? So yeah, that's the key community update, and that should set the context of what we are describing next in the YARN piece as well as in the HDFS piece. So now Zian will take over and walk us through some of the YARN level stuff. I'll come back and cover some of the areas too. Any questions before we move forward? We do want to make this interactive and get to know you also as part of this process.
So, I know we got one, but what are HDP? Hortonworks data platform.
So this is a community Hadoop meetup, so I would keep the HTTP ones. Yeah, yeah. Yeah, I'll leave it at that. Okay. Yeah, we could talk offline on what's happening. Of course, there's a major, all the Hadoop distributions, of course, have different release trains, and they pick up various versions, not just for Hadoop, but think Hive, Spark, HBase, Kafka, and so on, right? It gets a little very vendor specific, so we should take that offline. Anything else? So actually, there one more thing I wanted to ask. So how many of you here are production Hadoop users? And Hadoop may mean, like I said, it may be one of these 25 projects in the constellation, right? How many of you are actually Hadoop users? Okay. And vendors. Users and vendors. Yeah, sure. It includes people who just use it or who actually supplies. Okay, that's good to know. How many of you actually contributed to Hadoop, either with patches, documentation, releases? Okay, little bit. Okay, good. So we do have some mix here. All right, that's good to know. So with that, I will hand off to Xian.
Okay, thank you very much for to go overview of the status of the Hadoop project. So right now I will give some details, what exciting features we have accomplished in Thread 0 and Thread 1. So basically we'll split to two parts. The first part is we focus on the platform themes, which includes like scaling, and usability. And another part is the workload themes, which focus on the containers, resources, and services. So when we look at the scale, the first one comes here is that actually tens of the clusters we made up is like they have a large amount of nodes. So we list some of the companies here. Actually, they are technical giants within the industry, and they do have a very large single cluster with a lot of nodes. So one of the examples here is we actually got the statistics that Microsoft have 50K nodes in one single cluster. So that's like a very fresh data we get from their latest blog post. So that's actually a very big challenge because we want to maintain this amount of resources within a single cluster. So we need to have a lot of things to deal with. And our roadmap is actually not stop here. We want to like further scale to like 100K or even beyond. So so the first solution comes here is that we use the YARN federation to solve this kind of problem. So basically what YARN federation means that we actually split this big cluster into several subclusters. And usually this big cluster have like 10 or 100K nodes, and we split to 3 pieces, and we call it subcluster. And then from the infrastructure point of view, we will have like this state store to negotiate with each of the subclusters because they all have their own resource manager and application master. So from the endpoint view, when end user trying to submit an application, actually he will like goes to the router to send a request to the state store. The state store will handle this request and final decision, make the decision which cluster, which rack, or in which node this application will locate in. So another aspect is that we have done several features for scheduling. So one of the things that is we move forward to build a more global and fast scheduling. That means that previously actually we have the old version of the scheduling that has several problems like we focus on one node at a time when we do the allocation. So we we will cause some of the sub-optimized solutions, but maybe that is not the overall optimized solutions. And another thing is that we may cause several coarse-grained logs. So these kind of issues we definitely want to avoid. So with this global scheduling, we can see that we improve several things like below. For example, we can look at several nodes at the same time. We can actually do it parallel, not sequentially. That improves the efficiency a lot of, several times. So there's another thing that we can use YARN scheduler to allocate. By doing this, we can use the YARN scheduler to allocate more than 3,000 containers per second. So that means we can do 10 million allocations per hour. That's a huge improvement compared with the old scheduling platforms. So let me give you a short example how this works. So basically, we have this global scheduling, and we have different threads going on, and each thread will have allocation proposal, and all these threads will actually look into the schedule state, and they will make their proposal based on the same state. But the good thing is that actually they do in parallel. So compared with the old one, we do it in sequential, one node at a time. We do it in parallel, so we have this amount of threads. We can improve the efficiency when we do the allocation. So after all these threads has their proposal, they will send it back to the placement committer, and the committer will aggregate all these proposals and submit the allocation at once. And another thing comes here is that we have the better placement strategies. So that means that actually we can do allocations for the job that might need to have all the components in the same rack, like we call it infinity. And another feature we want to do in the opposite, which is anti-infinity, which means that sometimes we want to spread some of the allocations to as many machines as possible to avoid the resource interferences. So another thing is that we allow to set the specific number of allocations per node, node group, which we call it cardinality. So here's the short example. We can see that how anti-affinity and affinity looks like. So affinity is pretty when we try to submit a storm application, we want to use a storm application to locate us near with the edge base as possible, so that we can have more efficient data reading, read out. And on the other side, sometimes we may need to enable the anti-affinity. For example, if we have edge base being set up, we don't want these region servers to be adhered to each other too close, which we can reduce the resource interfaces. So another thing is that we want to introduce absolute resource configuration in capacity scheduler. So in origin, we do have the resource capacity calculated by the relatively percentage. So for example, if we set up one of the queues that capacity is 50, that means actually we can take up to 50% of the parent queue. But sometimes we do have this scenario. We want to give me X amount of resources. I want this to be absolute value, but not X percentage. So we need to meet this kind of requirements, and we can directly give the absolute resource when we do the queue mapping and do the allocation. So given this opportunity, actually we can do we can address another problem, which is previously, since we set the percentage for all the resource types, so there's single percentage value for all the resource types. But when we do the absolute resources, actually we can solve this problem. We can avoid this kind of thing happen to make this more flexible. And another good features is that we have auto creation of the leaf queues. So this feature is actually focused on when we want to tie the user to the one of the queues. We do the queue mapping. So for example, if the user X comes in, and we can automatically create the queue for this user, and we can use this queue while we do the queue mapping, and we can clean up the queue right after we used it. So this more dynamically, we can set the queue hierarchy and queue mapping, compared with the previous always that we need to set all the queue mappings and queue configurations priority to all the things set up. So that's the very good thing for us to make dynamic creation of the leaf queues. And the last thing goes is that we want to focus on some of the features we use for the usability. So one of these is that we do have the API-based queue management being implemented. So what this means is that previously, when we want to change any of the properties or the values from the queue management or queue settings, we want to do it by changing the XML files. But within these APIs, actually, we can call the REST API to change some of the parts by doing the REST API core. So that makes us more flexible to make the changes on the fly when we after we deploy all the queues, after we set up all the queue mappings. So this is one thing. Another thing is that we did a lot of improvement and enhancement for the log management. Actually, not just related, not just limited to this Jira. Actually, we have a lot of other Jiras coming to focus on this part and basically let the user to see the logs and do the log analysis more efficiently. So another key feature is absolutely focus on the user experience and the user interface. So actually, we announced the new version of the UI, which is UI2. So basically, the idea is that we add a lot of data visualization features so that we can see there's a lot of charts when we go to the UI to see some of the statistics and the status of the cluster usage. So that helps the user to see it more efficiently and more clearly. So this is another example. Actually, we go to some of the detailed pages and we see more detailed statistics list here. So the last thing here for the usability is that we implemented the timeline server version 2. So the idea is that actually previously we have the old version of the timeline service. That version actually had some scalability issues. So we also can see that understanding and monitoring Hadoop cluster is actually itself is a big data problem. So we want to address this problem by monitor the cluster more efficiently. So we introduced the version 2 of the timeline service, and we use the HBase of the backend to do the better scalability and for the read and write. So and another thing is that we also care about the backward capability. So we integration with the version 1.5, and we handle this kind of thing very well. So that's all the features for the platform themes, and I'll hand it over to Vinod for introduce some of the workload themes we have for the features.
I'll just use this. Can you confirm if it's working? This one's good. Okay. All right. Real quick, containers. I'm sure everybody have heard about Docker. So containers have been around for a long time in Linux. Clearly, Docker is one of the projects that popularized containers by making it very accessible to use, easy to use, and the image format that Docker brought in, of course, has become an industry standard, right? We've started looking at, YARN historically has run workloads like MapReduce, Stay, Spark, Flink, LLAP, and so on, right? But the containers that YARN had were essentially Linux process and process trees, right? When Docker came along, circa 2002, 2003, we started looking at, hey, can we actually package things differently in terms of Docker images as opposed to jars and tarballs and so on, right? This effort has been going on in the community for a long time. We went through a couple of rewrites, and this feature actually became a GA feature in the 3x time frame. We implemented this feature in YARN by adding a notion of a container runtime. So you have the age-old process runtime that would be used for your MapReduce, the Spark workloads, but you can also have a parallel Docker runtime using which a user can bring a Docker image and tell YARN to say, hey, run 10 copies of it, and using my MapReduce library, my Spark library, or you can do things like TensorFlow or one of these newer applications, right? Because people have built a lot of applications, images in Docker, and they have large multi-tenant Hadoop clusters, right? Putting those two together, how can we actually enable people to write, either write new applications easily or bring their existing applications which they've already containerized? That was the goal of this exercise, right? So using this feature, you can run applications with Docker and without Docker on the same cluster. There are a bunch of security-related caveats. The open source documentation talks about some of them. But with those caveats, you can run a Spark application running on YARN, along with a TensorFlow application or an HBase application, which is containerized and Dockerized. You would not lose any of the scheduling functionality that we had built in YARN for years. You can actually set quotas and say, hey, this user is going to create 10 Dockerized applications. Limit them to only use 500 GB of RAM in my cluster, right? That sort of scheduling and resource management primitives continue to apply uniformly whether you're running a Dockerized app or a non-Dockerized app, right? So that's the work we did in the framework. And to showcase how you can use it, very recently, a few months ago, we actually did a small POC, and hey, Milind, I didn't see you come in. Sorry about that. I was just doing a survey. Who was around last year hug? Maybe I should do a survey. Who was at the first hug? Long time. So we did a sort of an experiment to basically say, bring your own image which has Python libraries or R libraries. And PySpark and Spark are very common ways of how people write their applications, right? So using the Dockerization feature in YARN, you can actually say use Spark version X and combine that with my Docker image, which has Python libraries and all the dependencies, or R libraries and all the dependencies. You can put those two together and run PySpark app or Spark or app on top of YARN in the same cluster where you are running the non-Dockerized ones. So as a package isolation, this is actually super powerful, right? Any questions? Actually, Zian might not have given you opportunity to ask questions. Any questions on any topic so far? Before we all forget the context.
I have a question regarding YARN.
Yeah. Sure, why not? Mm-hmm.
So they decided to do their own resource manager.
Okay.
It's a multi-tenanted environment and very difficult. So they decided to do their own and they're not using YARN. Any insight on why that happened?
So I'll try to summarize the question. So yeah, I'll repeat the question, yes. To the understanding that I have. So Salesforce is using Spark and they've written their own resource manager to run Spark. I see. I have not seen it. I don't know if, have you guys seen it? So in general, applications run on platforms, right? And Spark runs on YARN, but there's a Spark standalone mode. There is Spark on Kubernetes. That's a recent project. And you're telling me there's one more resource manager. We'll have to see. The question was, why are they running it? Why are they not running it on YARN? And sometimes it's technical reasons, and sometimes there are non-technical. Okay, so we'll. We should zoom into it. I don't have enough information to answer. I see. Okay. Unfortunately, I don't think I can answer that question without understanding it. Makes sense. Yeah, yeah. All right. Anything else? Yeah, there's one and then we can do that. Beautiful. So the question is, how does data locality work with Docker applications, right? So if I don't have Docker applications, Hadoop, when I say Hadoop, HDFS and YARN, they have a notion of network topology, right? So within the brains of Hadoop, it knows what is a machine, which rack does it belong to, or if something doesn't belong to the rack, in the brains of name node, in the brains of resource manager, it knows, right? So if I talk about Spark without Docker containers, the way it works is on the Spark shell, it basically goes to name node and asks, hey, where are my blocks? When it gets the block information, it passes it along to Spark, right? Funny thing, even without Docker, Spark has a bunch of locality problems because the use case for Spark is just bring up 10 containers. I don't care where they're coming up, right? Bring up 10 containers on 10 random machines. And within that context of Spark, I'm going to run an application. And that application may, in the first iteration, read data on these 3 machines. And second iteration may read from 10 other machines, right? So in a sense, I'm saying Spark, even without containers, there's a notion of loss of locality because it's a static session you've created, right? Compare that to things like MapReduce and Hive, where they're not actually creating sessions. Every Hive query actually goes and runs a bunch of containers and shuts them down, right? So let me explain Docker with that. If I actually run a Hive Thais query inside the context of Docker, locality still works exactly the same way. YARN will place the container on the machine where your blocks are, right? There's still one more caveat to that. If the container is running on the host machine, HDFS has this notion of local short circuit rate, right? Without Docker containers, this Hive Thais query or MapReduce query can directly open a short circuit to the data node and start reading data. That's where the locality performance comes in, right? With Docker, if you really want to make that work, we have to mount the socket inside the Docker image. Otherwise, you'll lose locality. So the same applies for things like HBase. If you want to run HBase inside Docker in a cluster and you want to access HDFS, you need to mount that socket. Long story short, locality still applies exactly the same way it does. But for some applications like Spark, Flink, where you actually do sessions as opposed to containers, locality doesn't matter anyways because you're just keeping 10 containers and doing whatever you're doing inside. Does that answer vaguely? Okay.
Can you expand more on that, opening up that socket for...
Expand more. So the way short circuit reads work is HDFS client and the data node talk through a Unix domain socket, right? And it's super fast. You're not going across the network stack. Both ends have the access to the socket. Without Docker, the process can directly access it because it's all in the same kernel space and the same machine, right? With Docker, we have to do additional magic to mount that socket in. Yeah.
So, a follow-on question related to this. Do you have a CMDB configuration management database that uses as a base for looking at all the locality? Suppose somebody requests a bunch of nodes. Manage directly in HBase, or how does it?
So configuration. So general question is configuration management for these is it applications or is it the services?
Yes, applications and services.
Turns out, I mean, everybody has a way to do configuration in their environments. So if you're installing HBase, either in container environment or not, it's kind of very, it has its own flavor. Like if you're using a management system like Ambari or Cloudera Manager or whatever management system that installs and sets up Hadoop-related services, they have their own worldview of how to do configuration. But there are a lot of people who don't use these management systems and use the age-old Puppet, Chef, and so on. And they use those systems to push configurations to Hadoop services. So it's kind of very specific to how people do it. There is no universal way of doing configurations.
Yeah, I understand.
Yeah.
So is there a concept with YARN 3?
That's a good question. So if I'm running, say Spark or TensorFlow or HBase in a containers work environment on YARN, is there a way I can send configurations to these containers, right? So I can answer that in one of the last sessions, last parts. Yeah, there is an answer to that.
So some of these look similar to Kubernetes functionality.
Right. Yes, yes. So containers, like I said, it's Docker. Kubernetes has taken the world by storm in the last year or so, right? There is a lot of convergence. There is a lot of competition in both of these areas. We can imagine things like I mentioned, right? Spark, the Apache Spark project released 3-4 months ago a way to run Spark on YARN existed for a long time. You can also run Spark on Kubernetes. So it's fairly new, but in general, Kubernetes, there's a much larger industry momentum and so on. So the way the Hadoop community and YARN community are looking at it is it's kind of based on workloads, right? We have been running some workloads. How do we run them better in a containerized world? That's how you look at it. We're also looking at newer workloads like TensorFlow. I have a couple of slides on that. But in general, how do containers and big data relate? It's actually a very deep topic. Some of my colleagues actually did a presentation at Hadoop Summit. We could actually do one of the sessions in the next meetups. So how does big data world relate to containers? Because even today, big data has been one little moment on this side, and containers was doing for stateless apps, HTTP servers, and so on, right? How do they come back together? What does it mean to run? Hadoop itself is a platform, and Kubernetes is a platform. How do I run Hadoop on Kubernetes? If so, what does it mean for HDFS? What does it mean for YARN? What does it mean for workloads? It's a very deep topic. I'm glad you asked the question. So we could actually get one of that sessions, as part of the next meetups. So I'm saying the answer is the next meetup. So I'm cheating here a bit.
There are some startups in Silicon Valley who are running Hadoop in containers.
Yes.
Big data, logging,
Right.
my question is, I don't think they're committed that code to YARN.
It's not really about YARN, right? I think we should slate this for that session. There is a lot of interesting stuff in the big data and containers. If you're impatient, you can actually go search for Hadoop Summit, DataWorks Summit 2018. Just search for big data and containers. It's all recorded video if you're impatient. Otherwise, I can get the same speakers to come and talk about it. There are lots of very nitty-gritty details in this area. Okay? All right. I think that's a good amount of questions. So moving on. We've also done a blog post about this. It's not just that the community has built container support in YARN. Internally inside Hortonworks, we have been using YARN 3.0 plus containers to actually test Hadoop itself. So we call it internally as YARN Cloud. It's a YARN-based container cloud. It kind of again looks like Kubernetes, and I'm sure some of you can make that connection, right? But the reason why we built it internally is to say, every time there is a new commit in the Apache Hadoop project, we want to make sure that patch is not breaking n things, right? So we actually dynamically bring up 10 Hadoop clusters, run a bunch of tests. So that sort of use case we have had for a long time. And previously we used to do on VMs. Now that we have Docker and containers, we're basically saying, hey, why don't I bring up a full-blown Hadoop cluster dynamically and inside containers and run some system tests and say whether the patch is looking okay or not, right? So this is one of the side use cases for containers. We didn't imagine that this was going to be one of the use cases, but we put 2 and 2 together, and we've been using it internally inside Hortonworks. We talked about it in the community too. Only for testing. We don't encourage. Again, this is similar to what you mentioned. Blue Data is doing. Bring up a Hadoop cluster dynamically on top of a container platform. I think they have their own container platform, right? So it kind of looks like that, but we've been using YARN 3.0 containers for something like this, right? I'll hand it off back to Zian to talk about a few things.
Okay, thanks, Vinod. So now I'll continue with the resources. We did add some support on this part. So the first thing is that actually we support different resource types like the GPU and FPGA on top of the previous supposed resource types. So previously, YARN only support memory and CPU, and we train to think about these things like support different resource types is like the foundation for any resource management platforms like YARN or Kubernetes or other competitors. So if we don't support GPU or FPGA, there's a lot of limitations we can further make YARN to stay updated and stay competitive. So we definitely want to do this kind of thing. And with this support, like for example, GPU, when the YARN can support GPU and manage GPU as a resource type, Actually, we can build a lot of beautiful stories on top of that. Like we can build, we can actually run machine learning jobs or deep learning jobs on top of YARN by supporting GPU as a resource type. So there will be a separate session later, we know we introduce, which is one of the projects we are working on right now, which is trying to build an easy-to-use deep learning framework on top of YARN. So that will, based on the GPU support, we done for this 3.0 release. So yeah, I already explained why we want to do that, and another thing is why we want to do the isolation for the GPU. Because right now, like multiple resources may use the single GPU, and they may have the conflicts when they submit the requirements to require the same amount of GPU resources. So we want to do the isolation and make sure that this kind of issues can be addressed, and we can cause the OM easily. So the main idea how we do the GPU isolation on YARN is that actually we do the granularity for per GPU devices, and we use C groups and Dockers to enforce this isolation. Okay, so this is a short picture that we can see from the overall architecture. We can how we do the volume mount when we do the GPU, and how these different systems interact with each other. And another thing is we also support FPGA on the YARN.
This question.
Yeah. Oh, please.
The GPU one.
Mm-hmm.
So how do you handle multiple jobs on that? Because unlike CPU, GPU guys don't like to be preempted,
Mm-hmm.
because we launch and we take the whole memory and then we run the whole thing and then we get it out and we run it. Because they don't like to do multiple things running.
So the granularity is per GPU device. The granularity is per GPU device. So we start a container, we say you have access to 1 or 2 GPU devices, and for the lifetime of that container will basically reserve those 2 GPUs.
Yeah, right.
And fundamentally because GPUs are not dividable further like CPU.
So you're giving it to a container.
We are giving it to a container.
Right.
Yes.
Right.
Running multiple of them and mess it up. Okay.
Yeah.
So you're giving it to a container.
We have to, yeah. GPU is not super granular like CPU, yeah. We have to give, and that's how, even NVIDIA basically says that, they talked about further granularity within the GPU, but that's something that doesn't exist today.
Okay, any questions before I go to next session?
Keep going.
Okay, so next resource types we support is FPGA. So similarly, we do the same thing for FPGA isolations.
Repeat the question. Yeah. So the question was GPU granularity. If I run an application, say TensorFlow, which needs GPUs, the question was, hey, GPUs cannot be divided further. How is it going to work? Can 2 applications use the same GPU device at the same time, or how does it work? That was the question. And the answer we were saying was, it's very it's not fine-grained. You give a GPU device, allocate a GPU device for a container, and for the lifetime of that container, that GPU is gone. That's how it's implemented in any system that uses GPUs right now. It's a fundamental limitation that we have today.
Okay, so continue with FPGA. So we do the similar thing. We also enable FPGA isolation on YARN, and we also use the C groups to enforce the isolation. And currently, only support the Intel OpenC SDK for FPGA. So we just want to make this happen first, and then we can extend to other SDKs as well. So so next session will be focused on the service, and I'll hand it over to Vinod to introduce some of the features.
Yeah, so we can very quickly talk through this. Some of this will answer your questions, right? So in addition to supporting containers, over time what we realized is bringing more workloads to a Hadoop cluster, a YARN cluster, needs to be easy. Like, there are only so many frameworks which got written natively for YARN. MapReduce, Stay, Spark, Flink. I can only count maybe 3 or 4 of them, right? What we realized is to be able to bring more and more workloads to your existing Hadoop clusters, it needs to be easy to write those applications, right? We had created a project called Slider. This was a while ago. It was sitting outside of Hadoop, and we did learn a lot of lessons there. That project was in Apache Incubator, and the end goal for that, it became a quote-unquote smaller submodule inside YARN itself in 3.0. So if you go download Apache Hadoop 3.0, you'll get MapReduce out of the box. We'll get HDFS, YARN. There are other things like Ozone that the storage team is going to cover later. But you'll also get this framework called YARN service framework. Using this YARN service framework, you can write a very simple spec file. And again, for those of you who have created Docker Compose files or Kubernetes spec files, it's kind of very similar to that. We came from the Slider world, and so you write a small JSON file describing your existing application. And whether you combine that with Docker or not, you can bring that application very easily on top of YARN. So that's the summary of YARN services. And Slider basically retired from Incubator, and it's now officially part of YARN. Along with that, we did a bunch of things to make things very easy. So I'll show you an example here. So I don't know if you can see from behind. So let me just, no, maybe you can. Can you see it from the last row? Okay, so this is an example of a Kafka application that runs on top of YARN using YARN services. The first line is the name of the application. We just call it Kafka App 1. We've created this notion of a lifetime. Like, if you go to today's Hadoop cluster, somebody can run a Spark application and they may never terminate it and wasting resources. We've seen that we needed a feature in the form of lifetime where you can say, I'm submitting this application, I'll run it only for 5 days. After 5 days, if I don't come in and extend the lifetime, you go kill it, right? So that's the second line there. I want to run this Kafka application for 3,600 hours. 3,600 seconds, so that's an hour. Only run this application for an hour. If I don't come in and destroy it by that time, you automatically destroy it, right? And inside that, we're defining a Kafka broker, and we're talking about 3 Kafka broker containers. How do you start it? You use a Docker image called Kafka 0.10.1, right? How do you start Kafka? You go HTTP current, Kafka broker, Kafka server start.sh. What resources will it use? I need 1 CPU and half a gig RAM, right? What configurations do I need for this Kafka broker? This is the Zookeeper connect ID, this is the Zookeeper session timeout, and listeners, and so on, right? By writing just this spec file and bringing a Docker image, you can very easily submit this to YARN service and say, go set up a 3-node Kafka cluster, right? So that's one. And after it gets installed, you can also flex it up. Suddenly from 3 containers, you want to grow it up to 5 containers, you run one more command, and it'll go from 3 to 5, and YARN will ultimately take care of finding resources in the cluster, starting this Docker image, creating the configuration, and starting the daemon, right? So that's the simple way to think of YARN services. There are efforts that are going on to do app upgrades. Once you've deployed this Kafka, maybe from 0.10.1, you want to go to 0.10.2. How do I actually upgrade this application in maybe even in a rolling upgrade fashion, right? So that's something that's happening right now in one of these features, Jira's. You can not only just do that from the command line, you can go to the Hadoop 3 YARN UI, and in the UI you can do the exact same thing that I described there. Create a Kafka TensorFlow app, set the queue name, set the version, create a component with its own Docker image, and you go click deploy. It'll just run it on top of YARN. You can do all of that from the Hadoop YARN user interface. Any questions on this? Yeah.
Do you have to set up Docker on the CentOS, the CentOS cluster before being able to go and into YARN and say I want to deploy these particular services as Docker?
So the question was, do I have to go set up Docker on the OS at the OS level before I can use this feature, right? Yeah. So we assume that Docker is set up. Of course, you have to tell us where Docker is installed, so we can go. We as in YARN can go and launch containers. You have the OS. You install Docker, and then you install Hadoop. You configure Hadoop to use Docker, and then the users can go submit applications to that cluster. I should say I didn't anticipate a question from that last bench. No offense. You can do the same thing through UI. The other thing we did is LLAP is one of the components inside Hive. And previously it was running using Slider on top of Yarn. We've translated that by working with the Hive community to run LLAP on top of Yarn services. So it takes advantage of all the latest and greatest things that we've done in the Hadoop 3.0 world. And last one, so I did briefly talk about this. We created this feature of application timeout so that there is less resource waste in the clusters. So using this, there are multiple things you can do. The app submitter can say, please run it only for 5 days and then kill it. But the queue administrator can also say, no application in this queue can run for more than 3 hours, right? So that way the administrator can avoid resource wastage by setting a max lifetime. And this is useful whether you use Docker or not, whether you use Yarn services or not. This is a very generic Yarn feature. I think I'll stop there and you can explain some of the 3.2 stuff. Or do you want me to just continue? Okay, I'll continue in the interest of time. So now, so far what we've talked about is already released in 3.1. There are a few things that are happening right now in the community. There's a tentative 3.2 release that's going to happen soon. And the Yarn part of it, there are a couple of features I would like to bring your quick attention to. One is called node attributes. We've seen a bunch of use cases where people say, in my cluster, on some machines, something is available, but not on the other machines. Think like JDKs. The admin has already a certified secure JDK 10, JDK 9, JDK 8 installed. And till now, there was no way to say, run this Spark application using JDK 10. But I don't want to, I want to use the JDK that's already installed by the admin, right? Using the node attributes feature, you can actually go create these attributes on every machine, saying it is CentOS 6.5 or CentOS 7.10. I'm making up numbers, 7.5, or JDK 10. Or you could also say, this has some software license that I have on these box. You can add these attributes on the nodes. And when the application comes in, it can say, hey, put me on a machine which has these attributes. So it's a very generic way of extending the core Yarn functionality to support these arbitrary location requirements, right? So that's something that's being actively worked on in the community. The last one is TensorFlow on Yarn. Again, using the Yarn services and Docker, we had done some experiments in the past to be able to run a TensorFlow app on the same Hadoop cluster where everything else is running. And people saw this and they realized, hey, we can actually do a bunch of additional things to make it super easy to run deep learning workloads on top of my Hadoop cluster. So that they dubbing it as Submarine. So Submarine is basically, think of it like a wrapper which makes running deep learning workloads in a Hadoop cluster super easy. It'll figure out security, it'll figure out HDFS connectivity and so on. And one of the engines is TensorFlow, and people are looking at plugging in other deep learning engines too. Yeah. So I didn't name this. So Submarine, they basically said deep learning, deep submarine. So that was the one. That's the linkage. I don't know if they documented that or not. I don't know whether those torpedoes are just whales. Yeah. Oh, wastage of resources. Lots of creative ideas in the room here. I won't stop you, but essentially this project can only happen now because we needed GPU support in Hadoop, we needed Docker support in Hadoop, we needed a way to easily bring up new apps on Hadoop, right? So this project is basically putting all of them together and making it super easy to run deep learning applications. And yeah, I don't have answers to what that is. I'll ask that in the community. But the one below is definitely a submarine. It looks like it to me. And yeah, this is an example right now. The wrapper is still super hard. You have to pass in a bunch of parameters. The workable implementation is happening right now. After that, you can very easily run deep learning applications. So this is before essentially Submarine. If you want to run a TensorFlow training application on top of Yarn, you have to do all of this. That's it. So we used 50 minutes completely. Any questions here before we move to the storage piece? Yeah.
Can you talk a little
Federation.
The federation part.
Federation, yeah. Go ahead. What is the question?
So before,
You should take it. Please go ahead with your question. I'll just bring it up.
so before you had, yeah, that's like.
Yeah.
Before you had one resource manager with the node manager. So you're now having multiple. Can you explain that more? Now you have concept of multiple resource managers and multiple node managers.
Yeah, so it's not actually super complex. I'll take it. It'll not take too much time. So think of this as your existing cluster. You have 500 nodes, 1,000 nodes, whatever. There's a node manager which is talking to the resource manager, right? So the way we are saying you scale your cluster to 50,000 machines. When I say we, I'm only just saying Microsoft. I don't think anybody else needs to run a 50,000 node YARN cluster today. But what they do is they have a smaller subcluster of 500 nodes. I'm just making some number. A 500 node subcell here. And then, these resource managers, there is a central state store. And, each of these node managers are augmented to say, run a container by talking to this resource manager or that resource manager. So I can actually run an application which can span 750 machines by using this mechanism. If you don't want to use it, you'll just restrict yourself to this line. You can submit an application to this RM, and let's say you only need 10 machines, that will just completely run here. The federation use case is, I have such a massive application that I need so many resources, but it needs 750 machines. At the same time, I don't want to have a single resource manager and 1,000 node managers because of scalability limitations, right? When you go to the 50,000 scale, like translate those numbers to say, this is 10,000, this is 10,000, and there are 5 of those, right? We have proved, I think it was Twitter who was running YARN with 8,500 nodes in one single cluster with one resource manager. So that's the known scalability to which people we know have already tested. Microsoft has this use case to say run it on 50,000 nodes, right? So for that, they extended the architecture to have these smaller cells. Each of these are 10,000 machines. It doesn't need to be, but that's the scale to which this will go. And then you combine multiple of those and run large applications. They say they have applications which span across that 10,000 node boundary. Like some massive query that touches a lot of data.
I think the AMRM proxy is the key here. It's installed in every node, which basically abstracts that you can talk to any number of RMs. With one cluster, it was only talking to one RM.
Yeah.
So that's how they expanded.
Yeah. So let's have him go. Yeah, please.
Like, how does this work? So this makes sense from a compute perspective.
Yeah.
How does it work with regards to like HDFS?
For storage, right?
Like, I'm just curious.
So storage definitely is scaled independently at this level of scale, right? Yeah, so it's scaled independently. Yeah, so it's a very good question. So again, the Microsoft use case, they have their own system, which is like, think of as your file system, right? It's one central massive store, and they can access data in all of in that storage system.
So this makes sense for compute, I mean, less so for HDFS, right?
HDFS itself has a different way of scaling using federation and so on. I don't know if are you guys touching federation in today's call? Not today. But you think of them as scaling independently. Compute is scaling independently because I might either need more storage or less storage. So we have to decouple that scaling independently at that point. And for Microsoft, I think they've talked about it publicly, so I can say it. So the storage there is not HDFS. They're talking about Microsoft storage like Azure. Think of it that way.
Would you use this for like MapReduce or Spark or Hadoop? Just wondering.
So Microsoft have, again, their own internal frameworks. They have this thing called scope. Yeah, non-Microsoft people, why would I use this? Only if you have a scale problem. If it's, yeah, it's only for compute scaling. Exactly, yeah. Yes.
So for each subcluster, can you have different job scheduling type? For example, one subcluster can have capacity schedulers.
Okay.
Another one would be like fair queuing.
So very good question. So so the question is, do all of these clusters need to behave the same in terms of scheduling? Like, is the policies here the same as policies here? Turns out when you actually go to this scale, you have to relax a lot of global constraints that we apply. Like in today's capacity scaler or phase scaler here, it's actually a global decision we are making. We are looking at all the resources that we have. We are looking at all the applications that are coming in, and we are doing a very tight decision, saying this guy cannot use more than this much, and so on, right? At this scale, you cannot actually enforce global invariants across these massive cells. So it's not just that they have different policies. Some of our existing policies need to relax. I'm not answering your question directly, but there's a lot of there's a lot of change in how you deal with scheduling policies when you go to this scale. It's no longer just do first in, first out here and fairness here. Because it's not possible, because there's one application that's submitted across clusters, and it cannot behave like first in, first out containers here and fairness containers here. There needs to be some sort of a global view, and once you have the global view, it cannot be as restrictive as it exists in the subcell, right? Again, there's a talk by the Microsoft guys about how scheduling will look like in such a massive scale environment. I'm punting off this question. Maybe in the meetup link I can respond and show you references. Okay. It's a very interesting topic. We should get you started. I'm sorry. We'll take the questions. Why don't you guys wire up so that we can get started on storage? Yeah, please. Yeah. Yes. 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 Independently, because what we've realized is you might want a node YARN cluster because you have lots of computing needs, but you might not need that many nodes in HDFS side, because maybe on a smaller set of nodes I can actually have enough storage, right? But I wanted to connect back to one of the questions that this gentleman asked. You would not only use this if you need 50,000 machines. Actually, there are use cases where I would use this on a smaller scale too. One of the examples is, for whatever reasons, I've decided that there are government, administrative reasons which are forcing me to create 200 node clusters as opposed to one 200 node YARN cluster, right? I would use this so that I have a 100 node YARN cluster here, 100 node YARN cluster here, but using federation, I have a global view across these two clusters. So I would not just use this for scale reasons. I would also use it for other, administrative policy reasons. People do spin up these clusters, but suddenly once you go to two different clusters, you lose the global view, right? Federation is actually giving that there's a global router, global view, using which I can see what's happening in this part, and so on, right? We do see that there is a use case beyond scale. Maybe I misspoke in that direction. There are use cases for like that, stuff like that. Okay. Any more questions we'll take offline. Thank you. Thank you for being patient. Yeah.
So is there any thought to go beyond that, like the serverless computing, like AWS Lambda, the scheduling that you over there, the call graph?
But if you're running outside of Hadoop clusters, we don't even control how the call graph look like. Yeah. You go to cloud at that point. Thank you.
Good evening, everyone. I'm Hanisha. I'm going to talk about new features in HDFS 3.x. We'll mainly cover 3 features: erasure coding, general node sync, and 3 name node support. Before we get into erasure coding, let's take a quick look into what the existing HDFS replication strategy looks like. HDFS tries to place one block replica on the same node as the client. In the figure here, the client is the second node on rack 1 with the smiley face. So, and HDFS tries to place the other 2 block replicas on 2 different data nodes on any one remote rack. So, with this approach, we get a fairly good data locality. Sorry. Sure. Okay. Sorry. So we get a fairly good data locality with this approach. Since the same replicas are placed on 3 different data nodes, across racks, the computation framework can take advantage of that and try to place the computations as close to the data as possible. Also, the block recoveries are fast. In case a replica is lost, we can just re-replicate using either of the other two replicas. One downside here is that we use 3 times the actual data size. So there's a 200% overhead for storing data. What erasure coding does is it splits a block into k data blocks and m parity blocks, and it can tolerate up to m failures. So for a 6+3 scheme, we have 6 data blocks and 3 parity blocks. The actual data is distributed over the data blocks, and the parity blocks are generated by encoding these data blocks using some encoding scheme such as Reed-Solomon. The disk space used for a Reed-Solomon 6+3 scheme is 1.5 times the actual data size. So compared to the 200% overhead we see in replication, 3 replica replication strategy, we have only 50% overhead for storage. We can also save some IO bandwidth on the write path. Instead of writing 3 replicas, we are essentially writing only 1.5 replica. So writes can be faster. Along with splitting the data into blocks, the blocks are further stripped into cells. So instead of writing the data contiguously, the first MB, a typical cell size is 1 MB. So the first MB is returned to block 1, the second MB to block 2, and so on till block 6. After that, we wrap around and write the 7th MB to block 1 again. This enables the client to write to multiple data nodes in parallel. Blocks B1 to B6 and P1 to P3 together constitute one block group here. However, there is no data locality for readers. For reading a file larger than the cell size, we would have to go over the network. Let's take a look at how block reconstruction is done for erasure coded blocks. Let's say we lose block B1. So to reconstruct B1, we would have to read 6 more blocks from the same block group. And once we get the 6 blocks, B1 can be reconstructed by decoding using the same scheme that was used to generate the parity blocks. So if we used Reed-Solomon for generating the parity blocks, we can use the same scheme to decode B1 from the other 6 blocks. Compared to the 3 replica strategy where block recovery is done by simply copying over the lost block from one of the replicas, block recovery for erasure coded blocks requires higher network bandwidth and also some extra processing. The write pipeline for replicated blocks happens in a serial fashion. So the client writes to data node 1. Data node 1 writes to data node 2, which in turn writes to data node 3. Also, we can read files that are being written to. The consistency guarantee for this strategy is that client can start reading from any replica and fail over to any other replica to read the same data. In contrast, the write pipeline for erasure coded files is more parallel. So the client writes to all 9 data nodes in parallel. And client can also, in this strategy also, client can start reading from any 6 of the 9 blocks. When reading from a data node fails, the client can fail over to any other remaining blocks to reconstruct the same data. In a regular replicated HDFS write pipeline, if one of the data node fails, the client will recruit a new data node, bring it up to speed, and add that node back to the write pipeline. But in case of erasure coded files, if a data node fails in the write pipeline, the client just ignores the failed data node and continues writing to the rest of the data nodes. The missing block is reconstructed later on. So in this approach, the write pipeline can only tolerate up to a maximum of m failures. M is the number of parity blocks. The general policy naming scheme followed for erasure coding policies is codex, for example, Reed-Solomon or RS for short, followed by the number of data blocks, followed by the number of parity blocks and the cell size in the end. So RS631024K denotes Reed-Solomon encoding with 6 data blocks, 3 parity blocks, and a cell size of 1 MB. Another thing to note here is that 2 blocks belonging to the same block group cannot reside on the same data node. And for that reason, for a scheme with K plus M, the K data blocks and M parity blocks, we would need K plus M data nodes at the minimum. Let's take a look at some of the caveats of erasure coding. First, as already mentioned, is the loss of read locality. All reads would have to use the network unless they are smaller than the cell size, and short circuit reads are not possible. Erasure coding is not recommended for very small clusters. So for a scheme of RS631024K, it is recommended to have 9 or more racks. Another caveat is it's not appropriate for slow writers that tend to keep the files open for long durations, say days or hours. This is because of increased probability of data node failures, and in case there are more than 3 data node failures, the write pipeline would fail. Block placement tries to distribute blocks over racks to increase to provide tolerance against rack failures. But this makes reads and writes off-rack operations, so cross-rack network usage would be higher. There are some technical limitations. Currently, erasure coding does not support in-place encoding. So if we wanted to change the policy of a file, say from RS63 to RS104, we would have to copy it or DCP it over to a folder with the new policy. It cannot be done in place. Currently, hflush and hsync are also not supported. So services such as hbase, which need these functionalities, cannot use erasure coding. Also, appends are also not supported currently. So files once closed are immutable. But we do recommend erasure coding for larger clusters or clusters with lots of cold data, or clusters having medium to large files. So erasure coding can be very useful for these clusters, especially when we want to reduce the storage overhead. Before we move on to journal node sync, are there any questions?
So, do you have any plans to add erasure coding for edge-based related append?
There are open JIRAs, but yeah, it's currently not available though.
Okay, but there are open JIRAs that we worked on later on. There's no plan. When is any timeline?
Some of the problems for supporting append, hard technical challenges actually. Also like teaming, supporting appends. The JIRAs have been open for a while for a reason, because they're hard technical problems to solve. So I do not hold out for a quick solution.
And another thing is we need to look at the use case. I mean, if the reason that erasure coding is useful is that if you have very large amount of data and you want to control operations.
Okay.
But many applications, and typically it is for cold data or private data.
Okay.
But edge-based like applications are hot data. And also if you look at largest edge-based clusters, they are like, okay, maximum maybe equal petabytes, small number of petabytes. So I mean, typically this feature we envision that people who would adopt are like they're talking about 20 petabyte, 50 petabyte, and then for them it becomes really important. For particularly for the data which is lying out there just for legal reasons, they have to keep it alive. So I don't see much demand as well.
Okay.
Let's move to the next feature, journal node sync. So if a journal node crashes and misses some log segments and then comes back up again, it will be re-added to the quorum on the next log roll. However, it might not have a complete history of the log segments. Let's take an example. Here we have 3 journal nodes, journal node 1, 2, and 3. And we start writing log segments to them. The first log segment from transactions 1 to 100 is written to all 3. And then journal node 2 goes down and misses the next log segment from 101 to 200. After this, let's say general node 2 comes back up again and general node 3 goes down. So now general node 3 will miss the next log segment 201 to 300. So even though there is a quorum maintained for each log segment individually, a general node itself can have gaps in its transaction history. General node sync was introduced to fill in these gaps. Let's see how the sync process takes place. Continuing with the previous example where general node 2 has a missing edit log segment, edits 101 to 200. So during a sync cycle, it would request general node 1 for its manifest. General node 1 sends its manifest with the list of edit logs that it has. General node 2 compares this manifest with its own manifest and realizes that it is missing one edit log segment. So it then requests general node 1 to send the missing log segment, and general node 1 just sends over the corresponding edit log. General node 2 adds it to its general storage directory and now is in sync with general node 1. That's how the sync process works. To enable this feature, we have to set the DFS general nodes enable sync config to true, and we can control the frequency of the syncs or checks using DFS general node sync interval. Are there any questions for general node sync? Okay.
Is the journal sync automatic?
I'm sorry?
So journal sync, that process is
Mhm.
automatic?
Yes, if we enable the, if we set the config key to true, it happens automatically.
In the config, the key was added because it's a new feature. So that eventually will make it required.
Okay. For high availability, the general setup used is 2 name nodes plus 3 general nodes. This setup can tolerate any one node failure. So to achieve higher degrees of fault tolerance, we can now have 3 name nodes combined with 5 general nodes. Out of the 3 name nodes, 1 would be active and the other 2 would be standby. The extra standby name node has the same functionality as the original standby name node in our 2 name node setup. It tails the edits on the active and can take up the role of the active in case a failover occurs. So the configuration is also very similar to that of a two name node setup. We just have to add another name node to the list of name nodes in HA setup. The DFS HA name nodes config key would have one more extra name node. We would also have to set up configs for the configs such as RPC address and HTTP addresses for the third name node, as we would do for the other 2 name nodes in the cluster. But that's, sorry, yeah.
So what happens if you have one active name node, 2 standby name node, and still remain the same 3 journal nodes instead of 5?
So if then the system would tolerate only one node failure. So if one of the 2 name nodes can fail over, but if more than one journal node fails, then we are again back to having the system down. So it's still possible to have that. It's just we wouldn't have the two node failure tolerance. Yeah, that's all I had for today. Any questions? Yes.
Subclusters in the name node, any thoughts on that?
I'm sorry.
Subclusters that previous presentation was about. We talked about subclusters, right?
So federated cluster.
Yes,
Okay.
yeah. And
Yeah.
then we need to talk about 3 name nodes here.
Mm-hmm.
So you want to touch on that aspect as well?
No, they are completely autonomous. So actually, federation is HDFS federation is a completely different topic, and the reason we have not brought it up today is because federation is not new to Apache Hadoop. It's been part of Apache Hadoop since at least 2012. So we have not touched upon federation. Maybe we can do a separate talk. Federation itself is a fairly large topic, so we can maybe do a separate talk that deep dives on HDFS federation. But no, this 3 node node is completely orthogonal from
Okay, thank you. I'll hand it over to Arpit now.
Right, so it's the end of the day. You guys must be all tired. Okay, so I will try to, let me see. Okay, got it. Thank you. All right, so I'll try to make this quick and interesting, and if you have any questions at any point, don't hesitate to stop me. So I'm going to talk a bit about Ozone, which some of us see as the future to solve the scalability problems with HDFS. Now, HDFS has served us really well and continues to serve us really well, scales very well. We have customers running more than 100 petabytes of storage on a single cluster, thousands of nodes, works great. But the one limitation of HDFS that you know if you work with HDFS at all is the number of files. And that's because HDFS has to store all of its files in the memory of a single name node. And so that means that there is a limitation on how many files you can store in HDFS. And typically, the name node starts hitting its bottlenecks around 300 to 400 million files, somewhere in that range. So what is Ozone? Ozone is an S3-like object store. It will ship as a separate, it is part of the Apache Hadoop code base, but it will ship as a separate module that you would install.
Could you repeat the question, please?
Yeah, so the question was that is Ozone going to be a part of Apache Hadoop 3.1? And the answer is no, it's not a part of Apache Hadoop 3.1. We will ship it as a separate module. Okay, so Ozone is an S3-like object store. If you have worked with S3, a lot of the Ozone concepts, APIs should look very familiar to you. It exposes a REST API and Hadoop RPC interfaces. We also ship something called Ozone file system, which is a Hadoop compatible file system. And a Hadoop compatible file system is basically just a shim layer that allows applications which understand Hadoop APIs to use the Ozone storage. So using this Hadoop compatible file system shim, it's possible today to use Hive, Spark along with Ozone, and in fact even run MapReduce jobs on top of Ozone. So the key user concepts very similar to Amazon S3, but we have an additional concept there called volume. An Ozone path looks like this: a volume, bucket, and a key. A volume is a unit of administration for us. Volumes are typically created only by administrators, and then they set quotas on volumes. You can have multiple buckets per volume, very similar to S3 buckets. A volume can have 0 or more buckets, and then you have keys within these buckets. Key names are unique within the keys. The volume key size can range from 0 bytes up. There's no hard-coded limit. And directories can be simulated using key names with / separator, just like Amazon. So, okay, so I touched a bit upon this. Why build Ozone? So HDFS is really successful, scales very well, but the namespace and there's a related problem. Block space scalability is really hard. And Hadoop community has proposed lots of good ideas to solve both of these problems. The first two up there are to solve the namespace scalability, and the last two to solve the block space scalability. One thing that all of these ideas have in common is that they are currently incompletely implemented. And the reason for that is it's really, really hard to change a working existing system that does things very well. And so it's like re-architecting a system is really hard. Sometimes it's easier to just build a new system. And actually, Ozone borrows lots of ideas from all of these previous proposals.
So some of the core tenets of Ozone, we want to provide strong consistency. We believe that strong consistency makes the life of applications much easier. We really have a pathological focus on having the architecture be simple, because we believe that one of the reasons for HDFS success is that it is a really simple architecture at heart. And this really comes into play when things go wrong. When things work well, everything is fine. But when things go wrong, you need to recover. Your cluster loses its power. You lose a rack. You lose multiple nodes. In those kind of edge scenarios, the simple architecture of HDFS really helps it recover quickly from kind of catastrophic situations. Like we have customers running 3,000 node clusters. They have a catastrophic event. They lose power. The nodes come back up within a few hours, couple of hours at the most, and everything is running back to normal. You don't have these days of recovery that you see with some other storage systems. And so that's kind of a really strong guiding principle for us. We want to have that same level of reliability and recovery with Ozone. Operational ease really falls from the previous point. Ozone should be easy to operate. I don't know if you guys would consider HDFS easy to operate or not. And another thing is that we want to use powerful building blocks wherever possible, and I'll touch more on this later. And the last thing is that it's really important that Ozone be completely open source, and it's been a part of Apache Hadoop since day one. So some of the key building blocks of Ozone, first of all, we are using Raft replication. So Raft is an algorithm for distributed consensus. It's very similar in spirit to Paxos, but it was designed to be much easier to understand. We did not design Raft, but we did have an open source implementation of Raft as part of Apache Ratis. That's a separate project. And the second thing is that we use this concept called storage containers, and containers is a highly overloaded term. So this has nothing to do with Linux containers or with Docker containers or YARN containers. So for containers, we use an off-the-shelf key value store, RocksDB. It's very similar to LevelDB from Google, but it adds a bunch of nice functionality that we can use. And then we built a distributed container management layer called HDDS. And I'll touch briefly upon HDDS, but we are using HDDS as one of our secret sauce. And on top of HDDS is then what we built, what we call Ozone. That's Ozone Manager. It's purely a namespace manager. And once you have the first three, building a distributed key value namespace on top of them becomes fairly straightforward. All right, so I'll go to each of these building blocks one at a time, and then we'll see how we use them to build up Ozone at the end. So we start out with storage containers, okay, yeah, not related to YARN or Linux containers. So a single storage container is very simple. It's just a collection of keys and values. It's a collection of blocks where the key is the name of the block and the value is the block data. The data is just a blob that's transparent to the container. The container doesn't care either about the name or about the data inside the block. And block names are unique only within a given container. And containers are the unit of replication, so we want to limit the size of a container. We typically limit it to 5 GB. And containers can be in two states. One is open, in which state the container is writable. You can write blocks into the container. And once the container is closed, at that point, it becomes immutable forever. And so the natural on-disk storage format that we use for containers is each container is basically a RocksDB database. And we had some optimizations for larger values because RocksDB and LevelDB are not very efficient when you're storing extremely large blobs. So then the next step is how do you take these containers and replicate them? And the way we replicate them is by using this is where the Raft protocol comes in. So each container has a set of replicas, and for us it's 3 replicas. And clients push their changes into these containers. And these changes are then, one of these replicas happens to be the Raft leader, and the remaining 2 are in the follower mode. And the client pushes these changes to the leader, and then the leader will transparently replicate them to the followers via consensus. So container operations are really simple. You can atomically write a key value pair, which is like a put key operation. You can read a key, you can delete a key. And this is pretty much the core operations of a container. So okay, now we have built these individual containers that can be replicated. So how do you tie all these containers together? And that's where the storage container manager comes in. So it's a centralized service that manages containers. And you have a question? Okay. So SCM can be, we call it the SCM. It can be used to allocate containers, delete containers. It listens for container reports from data nodes. And if it loses copies, then it creates additional copies to maintain the replication. And the key thing is that SCM does not know about the contents of these containers, and it doesn't really care. I mean, it only knows about the containers. It doesn't know what blocks are stored inside the containers. And this is kind of the key to solving the block space scalability problem that we have with HDFS. So putting it all together, containers and SCM together give us what we call HDDS, that's the Hadoop Distributed Data Store. And it's just a pure container-based storage layer without a namespace. So you have the storage container manager, then you have the individual data nodes, which are the same data nodes that we have today in HDFS, and they store the container replicas that are replicated using Apache Ratis. And so at this point, we still haven't talked about the Ozone at all or the namespace. All we have built up to now is a distributed container layer. And the key thing is that this container layer can now be used as a building block to build any distributed file system on top. So Ozone is just one implementation of a distributed file system that sits on top of this layer. In theory, you can rewrite, there is in fact a design doc out there to rewrite HDFS to leverage this container layer. So that solves the block space scalability problem for HDFS by delegating it to this container layer. Another option is something that we are just internally calling Quadra, which is like mountable iSCSI volumes backed by HDDS containers. And you can build your own namespace on top of it. We are optimistic that people will use this container layer to build their own distributed namespace. Any questions so far? I know I'm going really fast, but if you have any questions. Yeah, RocksDB is a project that came out of Facebook. It's an open source project. So what RocksDB, what they did was they built on top of LevelDB, and they tried to make RocksDB more easy to use in a distributed system. So actually the RocksDB use case was pretty much what we are using it for. So they have some nice facilities like snapshotting, incremental replication. So like you can take two snapshots and then incrementally replay all the changes on that snapshot remotely. So those kind of facilities are really useful to us because we are using it exactly to build a distributed container store. Also, I think they have done some additional performance improvements on top of LevelDB, but I believe they took the LevelDB source code from Google and built on top of that.
So RocksDB already uses Ratis?
No, RocksDB does not use Ratis, but it's just a key value store that provides these primitives like snapshot, replay, and then on top of that, we use Ratis to build the distributed part.
I think in RocksDB, they are trying to put it on MySQL as well in certain areas.
Okay, I'm not. All right, I'll continue. Okay, so then the next question is how do you build Ozone on top of HDDS? And at this point, it becomes really simple. Just add one additional service, and that's an Ozone manager. And Ozone manager is just a service that provides a global key value namespace. It's a really simple service. You can put keys into it and delete keys from it. And each key is a sequence of blocks that are stored in HDDS. And the nice thing about the namespace is that it has a locality of reference. So that means Ozone Manager can support a namespace of tens of billions of objects. And not all of that needs to be cached in RAM like the name node. Only the working set needs to be in RAM. So the scalability of the Ozone Manager is not limited by how much memory you can have or how much heap you can manage. And how do we implement Ozone Manager? Again, we use RocksDB. So we use RocksDB as our key value store for storing the global namespace. And the Ozone Manager instances will be an HA service. Currently, we don't have HA support, but it will be an HA service. And again, they'll be replicated using Ratis. Yeah, so when we put all the pieces together, you have Ozone Manager, replicated service talking to SCM, also a replicated service talking to thousands of data nodes. And similar to HDFS Federation, you can have a shared storage layer of HDDS and put multiple namespaces on top. So you can have multiple Ozone managers. So in case you feel that one Ozone manager, either the namespace is becoming too large or it cannot serve the performance, then you can have multiple Ozone manager implementations. And on the second slide, we talked about volumes. So you can partition your volumes across Ozone managers. Okay, so current status of Ozone, we are planning for an alpha release in September, and there are multiple areas where we are doing active development with the community, high availability, Kerberos security. We are working very hard on robustness, so we want to bring Ozone to the same level of reliability and robustness as HDFS has today. You can in HDFS, you lose a node, nobody even cares. You lose a rack, it's often just a blip. So HDFS continues to keep functioning, and we want to get Ozone there. So there's a lot of work that we are doing to get there. And we are also focusing hard on performance and scale. So we want to get HDFS to Ozone to the same level of read-write performance as HDFS, which is HDFS can pretty much max out your disk or network speed, and that's kind of our target goal with Ozone 2. So yeah, so this is the slide where I encourage contributions. So we would love to get contributions from more people in the Hadoop community on Ozone. It's a new file system. There's a lot of exciting features under development and a lot of areas to contribute on. And you can contribute code, unit tests, acceptance tests, documentation, or just download it, try it, and report bugs. So there's some links, resources, some links I have up here. And I think the talk is recorded in case you want to get at these links later. So we have a website for Ozone. We have some instructions on the wiki page, and also as part of our inbuilt documentation, how to download, build, run Ozone inside Docker containers. And then if you want to get started trying out fixing some of the bugs, you can go to the Apache Jira tracking and look for all the open bugs. Okay, yeah, and if you need help, like if our docs are not helpful, or if you have not contributed to Apache Hadoop before, then you can email the Apache Hadoop HDFS mailing list or contact any one of us directly. Arpit, that's me, and Jitendra is sitting here, and Anu is one of our team members who works out of Seattle. Any of us would be happy to help you out. All right, that's all. So any questions?